Hello everybody, welcome to our final class in our Introduction to Deep Learning course. Today we're going to be covering Getting Started with Torch. We presented to you by Allison Lowndes. As with our previous classes, you are welcome to ask questions directly in the chat window. We have a group of our experts online to help answer. They will answer your question and then rebroadcast the question and answer so everyone can see. We will not be taking audio questions, and if we don't get to your questions, we will have an office hours next week where after taking the associated hands-on lab, you can continue to ask more questions related to Torch. As with all our previous recordings, this will be posted to our Deep Learning course website, which we'll post here shortly. You can find all the prior recordings as well as slides and links to the hands-on labs. And I encourage you to take the labs if you haven't yet, because they are going to be free until for another 2 weeks while we finish up this course. So if you haven't taken them, now's a good time to do it while they're still free. So I think that's it. Allison, why don't you go ahead and take it away?
Okay, thank you very much, and welcome. Thanks for joining our 5th class in the Deep Learning series. I'm actually based in Bristol right now in the UK, but I'm actually from the north of England, Manchester, hence the accent. So wherever you are in the world, hi. I'm going to assume that everyone listening has already gone through the previous 4 classes. If you haven't, as Mark said, I'd highly recommend that you do. I realise live is fun, but this is being recorded, so you can come back anytime. So quick agenda. I'll just mention obviously the previous classes, cover a little bit about iTorch, and a reminder of why deep learning. Then we'll go through some preliminary introductions on Torch and the benefits, a little bit of information on installation, and more on the theoretical side, and then go through again the current facility we have for Quit Labs, and some more information on software releases, roadmaps, and then there will be some advanced intel for you later on. So I do have a slight delay when I'm actually changing slides, so just bear with me on that. So as Mark mentioned, also live now is our corresponding hands-on lab, and you can actually use this presentation material as a reference if you wish, but the labs are self-explanatory. If you are coming in cold, all of the classes and hands-on labs are online. Quit Labs uses IPython notebooks, and we're running the same AWS, Amazon Web Services, GPU instance, so it just takes around 3 or 4 minutes to set up the environment. Everything runs on the cloud, not on your computer, so there's no need to download any code right now. So you can either go to the developer zone for all your info, or simply go to Google and say, or type NVIDIA Deep Learning to be directed to all the resources that you'll need. These slides will be put up on the actual course site. So IPython notebooks are really great, but Torch thought that they could be better. So they actually wrote iTorch, which is an IPython kernel for Torch, enhancing your browser experience even further with videos and images and embeddings. So quick reminder, we have covered a lot of material in the previous 4 classes. So why we're here is to learn how to teach a machine to see and hear, but also to learn what it's both seeing and hearing. So not doing anything by brute force, this is learning. I'm actually a deep learning solutions architect here at NVIDIA, so I have this fantastic job of seeing applications across the board in this incredible artificial intelligence field. So we have image classification, localization, action recognition, speech translation. In the in-car tech area, we have pedestrian detection. My personal research was on medical imagery and finding features within medical images, and deep learning is all capable of doing this. So let's get going. Torch started around 2000 with Facebook's Ronan Colabert, the main developer. Torch7 is the current version, the fourth. They use odd numbers only, so 1, 3, 5, 7 being the fourth. And this version is aimed at web-scale learning in speech, image, and video applications. Torch is used exclusively for research and prototyping for unsupervised and supervised learning, reinforcement learning, and more. It's real state-of-the-art code. Facebook especially spends a great deal of time improving parallelism for multi-GPU, model, data, DAG, directed acyclic graphs, and overlapping techniques to improve host device communication. Plus, there's lots of development in kernel speed for convolutions, etc. So current maintainers are Ronan Colabert, who's at Facebook, Clement Farabee, who is now at Twitter. You may know him from his MadBits site, which Twitter then acquired. Corey is at DeepMind, or Google DeepMind, and Sumit Chintala is at Facebook in Facebook's AI lab. Torch is widely used in many research labs and companies, including obviously Facebook, Google, Twitter, but also NYU, the IDEAP Research Institute at Purdue, Element Inc., and Wet Lab. So the first thing I would advise you is to jump straight to the cheat sheet. Life is busy. Coders figured out efficiency a long time ago. Torch is maintained by top coders, way more ninja than I am. So I'll actually be using some of their material in both this presentation and particularly in the hands-on lab. They are all very happy to offer this assistance because they want you using their highly optimized framework, Torch7. The cheat sheet and all the code are maintained on GitHub, but if you do have advanced questions only, you can head over to Gitter, where most of the devs hang out. But please, for install or newbie questions, go to the Google group first for very quick responses. The community behind Torch is extremely good, but they do need to split the support workload. So Google groups for install and new queries, Gitter for chat and advanced questions, or just to hang out and watch some real master coders at work. So why Torch? Basically, Torch is built on Lua, which is a scripting language, a very quick scripting language. It allows for complex applications to be compiled and optimized, but it's also embeddable into any environment, iPhone, video games, web backends. The complete Torch framework can run on an iPhone with no mods to scripts whatsoever. Torch's universal data structure, the table, can also be used as an array, a dictionary, hash table, class, struct, object, or list. Torch7 extends the table with a tensor object. We'll go further into tensors later, but you should have heard about them already in previous classes. This is an n-dimensional array type. For training neural nets, autocoders, linear regression, convolutional neural nets, recurrent neural nets, etc., it's all about gradients and loss functions, and Torch's NN package provides it all. It's also extremely simple to recast predefined models, switching to GPU. It's as simple as the slide shows, model, CUDA, and defining inputs as a CUDA tensor. If runtime speed is a priority for you, if the convenience of a very easy to use scripting interface is a priority for you, and definitely if you need to use multi-GPU, then Torch should be the choice of framework. So more benefits again. Very efficient tensor library, similar to NumPy, with CUDA for neural network computations. A dedicated NN package for directed acyclic computation. Again, I'll stress, really great community and industry support. Several hundred community-built maintained packages. We'll go into that in a few more slides. It's in very active use for state-of-the-art neural network research. So therefore, already has fast, efficient, easy-to-use multi-GPU support. It's also, as all the maintainers will tell you, has an awesome interface to see via the Lua scripting language. Very fast due to the just-in-time compilation. It's also very easy to learn, but right from the word go, the reason they liked it is simply because it's embeddable and currently has ports to iOS, Android, even FPGA backends. So again, it's the support that you get from Torch. I personally got loads of help when I first started using this, and I've coded in Python, C, C++, Java, even a bit of Haskell, but Lua was just trivial. So just try it. Okay, so the Torch core consists of the following packages. Each package repository usually includes its own documentation with a README, which may contain links to the docs directory. There are many packages, Torch, and then I won't bother going through that entire list. We'll talk about the TREPL later. So a bit more information on Lua. This actually originated in Brazil. It's very powerful, fast, lightweight, and again, it's because of its embeddable nature that it was picked out. It combines simple procedural syntax. It's dynamically typed. It runs by interpreting bytecode for register-based virtual machines, has automatic memory management with incremental garbage collection. It's actually maintained by a team at PUC Rio. That's the Pontifical Catholic University of Rio de Janeiro in Brazil. And it's actually now housed at Lab Lua, I believe, which is a laboratory of the computer science department there. It offers excellent support for OOP, for object-oriented programming, also for functional programming and data-driven programming. Its table implements associative arrays in a very efficient manner. That's an array that can be indexed not only with numbers but also with strings or any other value of the language. Tables actually have no fixed size. They can be resized dynamically. They can even be used as virtual tables over another table to simulate various OO paradigms. Tables, in fact, are the only data structuring mechanism in Lua, or rather Lua 4 now. So it's very powerful. And the tables themselves are used to represent ordinary arrays, etc. So Lua itself comes with a very handy package manager called Lua Rocks. The packages are colloquially known as rocks. Different demos and tutorials rely on different third-party packages. So if a demo crashes because it can't find a package, then simply install it using Lua Rocks, as in the code here. And there are many. I'll list a few, but there's actually hundreds. So for general maths, you have the standard Torch package. Cephes is the mathematical functions library, which it was actually is the heart of SciPy, which you'll probably already be familiar with. Graph, obvious. NumPy is the random kit. Signal includes FFT, Hilbert. There are many different data formats supported. So CSVGO is a CSV library. You have Lua CJSON for fast encoding parsing. MatTorch, MIDI for reading, writing, and manipulating MIDI data. Audio, image, obviously. Graphics Magic, if anybody uses the Graphics Magic API. Of course, it has machine learning with NN, the domain neural network package. NN Graph provides graphical computation. DP is the deep learning library for streamlining research and development. DPNN is the deep extensions to NN, which provides things like reverse table. NN Inception, if you're all familiar with those graphical plays that have been going on around the internet recently. It also has RNN, obviously recurrent neural network library. UNSUP is a package for unsupervised learning in Torch. Manifold to manipulate manifolds, component analysis, and also reinforcement learning, which of course is still evolving. For visualization, we already know about iTorch, but it has Qt Torch, also display. For computer vision, you have FEX, which is feature extraction. That's if you're SIFT people and you still want to play with those handcrafting modules. Natural language progression, again, NN, RNN. Senna, this used to be a state-of-the-art, so that's in there in the NLP rocks. And you have many distributed computing, parallel processing with simple names like parallel and threads, which is one of Ronan Colbert's original ones. This allows trivial data sharing between the actual threads. And I also picked out just a few random picks just to show you just the widths and breadths of this, but you have LuaSec, which is a binding for OpenSSL library, so you can provide SSL communication over LuaSocket. LMDB Torch, obviously an LMDB wrapper. CL Torch is the OpenCL implementation, or CLNN for the OpenCL neural network implementation. And as I said, just many, many more. So for installation, I believe the current workload is shared as follows. Twitter's Clement Farabee maintains the iOS. Sumit Chintala maintains the Android. There's even an instant launcher from the Torch site to an AWS instance like we use in the hands-on lab. So if you want to continue playing the easy option with a predefined environment, then you can actually use that. And again, the cheat sheet also offers Docker images for currently both Torch7 and 6.5. Of course, that will be updated accordingly. It has a long list of easy dataset loaders and install sites, since obviously you can't do deep learning without data. I personally jumped straight into Facebook's FP code, which again, and this, obviously I think most people know this, but requires a minimum Ubuntu 14.04 and a CUDA capable machine or NVIDIA GPU. Some have tried to do deep learning on Windows, but I always say resistance is futile. Stick with Linux, Ubuntu 14.04, and you shouldn't have any problems. I believe there are groups out there that are trying to do CUDA ConvNet 2 on Windows, but I'll leave you to it. So command line installs extremely simple. On this particular code here, the first script installs the basic package dependencies that LuaJIT and Torch require. The second script installs LuaJIT and LuaRocks, and then LuaRocks, the package manager, will install the core packages like Torch, NN, paths, and a few other packages. So the Torch ecosystem itself relies on LuaRocks for package distribution. Each is distributed via a Git repo, and Torch7 relies on that LuaJIT dynamic interpreter, similar to Python, but it's got very high flexibility and interoperability with an unmatched, some would say, assembler-written, state-of-the-art low memory footprint. The raw LuaJIT interpreter is actually very basic. So a package was developed called TREPL, a Torch read eval print loop, or REPL or shell, and that's just packed full of convenient features like tab completion on nested namespaces, history, which is preserved between sessions, auto print after eval, that can be stopped with a semicolon as standard. Each command is profiled, timing is reported. It's just very easy and very intuitive. So once installed, you simply run Torch with TH to start the TREPL. And for example, in this code on the slide, it's just TH and then your actual file name, and then you tell it where the actual data is residing. You tell it how many GPUs you're using, tell it which backend you're using, and which model that you're going to train with. It's as simple as that. So this is obviously a screenshot. It's a bit difficult. I hope you can see this. Alternately, you will be given PDFs of all these slides anyway. It's quite difficult sticking even a small entire neural network program into one screen. But neural networks in Torch are constructed basically using the NN package. Modules are the bricks, as Sumit says, used to build the networks, but each of themselves are neural networks. So they can all be combined with other networks, and then you can also bring in containers to create really complex neural networks. So for example, LeNet is a simple feed-forward network, takes the input, feeds it through several layers, one after the other, and then finally gives the output. And such a network container is, as this code shows in the screenshot, NN sequential, which basically feeds the input through several layers. So obviously QDNN is a big part of this, and vast improvements, to be honest, have been brought to deep learning simply thanks to not only our developers and the QDNN library, but for the simple fact that we work closely with Torch. We work closely with all the other frameworks as well. But QDNN is integrated deep into Torch with bindings from Facebook's AI research for deep learning and convolutional nets. So much that there is just really highly RAM efficiency on GPU. The best progress is made through collaboration, and obviously we're happy to be offering direct support for deep learning, but it is a collaboration. This is Sumit Chintala of Facebook. His interface to QDNN for Torch7 allows you to use QDNN as one of the highly efficient ConvNet backends, exploiting parallelization over multiple GPUs, FFT. Facebook used to have the quickest FFT out there. I mean, that was probably March, but people will be battling for that one. Custom CUDA kernels, and there are loads of other tricks. Alex Krzyzewski's CUDA ConvNet 2, Kemet Farabay's NN spatial convolution module, for example. And it's all available up on especially on Sumit's GitHub. He does hold most of the code there, and it's all open source. So just go grab it and train with it. So a little bit more detail on tensors. You should be aware of it now because we have covered it in previous classes, but it is the most important in Torch. Quick reminder, obviously, it is a serializable, potentially multi-dimensional matrix, but basically the number of dimensions is unlimited, and this is due to the long storage. There are several types of tensors that are all self-explanatory. Byte tensors for unsigned characters, char tensor for signed, short, int, float, double tensor, self-explanatory. A tensor, if you think of it in this way, it's helpful in the theoretical sense that a tensor is a particular way of viewing a storage, which only represents a chunk of memory, while the tensor itself interprets that chunk of memory as having the actual dimensions. So it can be easily manipulated within Torch itself. So moving on, you can learn more. Jorg Ostrovsky at DeepMind, I believe he's still at DeepMind, has a really excellent tutorial to really fully understand the theory behind the tensors. The actual data is contained in what's called a storage, and this is how Lua accesses the memory of a C pointer or an array. Storages can also map the contents of a file to memory. obviously because it's an array of basic seed types. I mentioned the classes previously, but the interesting thing about tensor factorization and the methods used specifically by, for example, Theano and CUDA, they all work on the basis that data has these unobserved properties seen in clustering, and patterns and behaviors that can be found with the 40-year-old techniques of expectation maximization or maximum likelihood learning. It all involves guessing and then updating parameters iteratively until a set threshold for significant results is met. Unfortunately, this technique is clearly non-convex. It produces different results each time, as there are an exponential number of regions in a problem space. We're dealing with massive problem spaces here, and a different number of regions that you may land in, many different local maxima. So finding the global maxima is very hard in this sense, but to efficiently find the same local maxima, you can now compute a large table of statistics and use them to recover the parameters which found that local maxima. So it essentially becomes an identifiable moment, should we call it. Simple matrix decomposition with tensors, therefore, essentially can now guarantee good results. But you can learn a lot more about this in as I said, in Jorg's tutorial. I'd recommend going and seeing it, and that's the GitHub there that leads to it. But again, we'll send these slides out, put them on up on the web. So CUDA itself, very simple. You simply require QTorch, QNN, or QNNX, which is an experimental implementation, or QDNN, which is the main QDNN bindings for Torch, clearly on a CUDA-capable machine. CUDA is just simply well suited to Torch, but it's because of Torch's flexibility and scalability that it's very impressive. So basically, you can even put any of this code with Torch on our embedded boards, and there are specific install and usage instructions at that link there, so you can actually work with our Jetson TK1 development kit with Torch and literally embed your code onto drones, onto phones. There's so many different applications. It's actually quite fun to work with. So have a play around on that. There's lots of tutorials, etc., to go into that further. So digits. At this point, all I can say is coming soon. We are working very hard on this. We have covered digits already in this course, so you should be familiar with what it is, our deep learning GPU training system. I would like to say no more than a couple of months, but as I said, developers are working really hard to get a beta out to you. And once that happens, then you'll have that full functionality of digits, which I can't stress enough. This is actually a screenshot of digits and Torch being run. Obviously, it looks quite similar to Caffe, but that's because it's the digits format. But this is raw Torch output, and I'll show you the logs as follows. But our developers are working really hard and around the clock to get this full integration for you. As I said, it will be very soon. So standard out logs are they're just extremely informative, especially if you then go into using FBQ and code. You just know everything that's going on. I know this is common across the board, but it just really is very informative for command line especially. So it's probably going to be fairly difficult for you to see all these, but again, slides will be sent to you. So standard out logs here. letting you know exactly what's going on behind the scenes, exactly what the code is doing, what the different timings. I'm not sure how many of you are actually already at this stage where you're running, but it definitely does help with the learning curve of understanding this until you actually get the kind of visualization that we can offer in Digits. And whether or not you've already played with Cafe and Digits, it does help to see that visualization side. But many logical coders would argue and say that the command line is better. So again, the actual Torch standard out is just extremely helpful. So an example neural network in Lua. Apologies for the tiny size again, but just going into a little bit more detail here. You've got the first layer applies 16 filters to the input map. I don't think I can do pointing here for you. So it's choosing randomly among different layers using the fan-in parameter, each times 5. The receptive field of this first layer is 5 by 5, and the maps produced by it are therefore 16 by 28 by 28. So this linear transform is then followed by tan-H nonlinearity and an L2 pooling function, as you can see from the code. So that pools regions of size 2 by 2. So stride of 2 by 2. The result of that operation is a 16 by 14 by 14 array. So that represents a 14 by 14 map of 16 dimensional feature vectors. The receptive field of each at this stage being 7 by 7. The second layer, similar to the first, except that now the 16 dimensional feature maps are projected into 256 dimension maps with a fully connected connection table. So each unit in the output array is influenced by a 4 by 5 by 5 neighborhood of features. Again, it's quite difficult to sort of tell you this in a presentation style, but it is worth. I always like to, literally go right through the code to figure this out, even if you're using out of the box code. So you've got this 4 by 5 by 5 neighborhood of features in the previous layer. That layer therefore has 4 by 256 by 5 by 5 trainable kernel weights, plus 256 biases. So the result of the complete layer, convolution and pooling, is a 5 by 5 array of 256 dimensional feature vectors, which is then flattened into a 6400 dimension vector and fed to the 2-layer neural net. So the final prediction, 10-dimensional distribution over classes, is influenced by a 32 by 32 neighborhood, and this is YUV pixels, basically, in this particular example. So you're defining color space. So as this slide shows, what I was actually working on was, and this is a sample of the Y-channel data, and this is the SVHN data set, which is the Street View house numbers data set from Google. A little bit more code for you to actually see. So you have TH and then the dual.lua. This is Clement Farabay's code. Again, he has some great tutorials on his MadBits site. This particular setting was size small, where you're basically testing on 10,000 images as opposed to 73,627, I think, by memory. Total images in the actual data set. Now, I actually stopped my own testing at 92, my own training, sorry, in code at 92.95. And the actual speed up, just for interest, from a 2.66 CPU, which is actually hyper-threaded to 12, was 19 minutes with a 4.75 speed up on a K40. So this, as I said, was my own testing, but there's lots more, and you can play with the SVHN code and train on our hands-on lab. So again, further help, And please ask for help. There is a large community of developers out there. As stated previously, please use the Google group for installation problems and newbie questions, because they're well used to answering them. There's lots of people using it, and it's a very helpful community. If you are advanced, head over to Gitter, and you can discuss with the actual developers and a whole lot more. But there is also a GitHub issues page that you can visit and get lots of extra help with. So the actual hands-on lab. Clearly, I can't do everything just in a presentation and by voice. So I would encourage you to go and try out our own lab. It's live now. It was actually enabled very much by Sumit at Facebook AI Research and Clement at Twitter. If you're not familiar, then take the time to actually just run through the video on the main Quick Labs page to understand how the lab environment loads. It will take 3 to 4 minutes to actually load anyway, so you get to learn how IPython notebooks work. But we are using iTorch in that actual hands-on lab. So if you haven't yet signed up for it, please do. It's as Mark said earlier, it's free until at least this deep learning course finishes. I would say possibly October. I'm not sure the actual date. Create an account. Literally go to the Getting Started with Torch7 lab and just click Start. It will load up the environment, and you can just take your time. I think you get up to 2 hours. There are certain requirements for the actual browser, but again, no code runs on your actual machine, and you're actually using an NVIDIA GPU in the instance. So as far as software releases go, all our supporting software is in constant development alongside Torch. I did say earlier that we work closely with them. So if you are signed up as developers on our developer zone online, you'll be informed at every release. The actual releases that we have has effectively doubled performance for deep learning now. With digits, once that comes online fully for Torch, multi-GPU scaling allows models to be trained literally up to 2 times faster. QDNN 3, 2 times faster for training with training support for larger models. CUDA 7.5 release again is 2 times larger data sets. So we're all working hard for you, and as I said, this is constant evolution of software as well as our hardware. Torch 2 are in constant evolution. So their current roadmap is for the NN container to have a unified interface between containers and graph. They are busily developing and optimizing the RNN package for recurrent neural nets. They intend to split the NN package into THNN and NN, so that THNN is a package using the REPL using TH as the backend, and NN would be the Lua layer. So THNN can then be used as a standalone C library, and the same for QNN. They're also intending to publish a lot more tutorials and working on a universal dataset API to support both GPU and CPU. Now that would be a fantastic tool, so I hope they can do that really quickly. They are putting together a model zoo as well, like Cafe, just to help people to get on board. So if you are beyond beginner, possibly even intermediate level, then we actually have Nicholas Leonard from Element Inc. doing an applied Torch7 webinar for us. This is October 8th, so I would recommend that you register now. That's the link there up on our main tech conference site. It's targeted at ML enthusiasts and researchers, and he'll basically be talking about not only classifying images but also building language models. Nicholas is a great speaker, so just register for that if you want even more information, because that will probably get booked up quite quick. And again, I will refer you back to the cheat sheet. This is the go-to place. Have that stuck in your favourites bar, because all the information that you need is linked to the cheat sheet itself. And again, these slides will be available pretty soon, if not now, on the DL course site. I would again just want, if I may say, that don't go to the actual Gitter just for install questions. Go to the Google group. So again, the deep learning course itself has already been run, but all the resources are online, all the slides, all the recordings, etc., and they will be there permanently, as much as that can go. So please check out the courses if you've come in cold into this one. And at that point, I will open up to try and answer some of your questions. So apologies if I do go quiet, but what I'm going to be doing is going over to the actual chat to actually read through your questions. Right, okay. Trying to figure out on the actual time. We've been going, just let me see. Right, okay, so in Torch, how 1D convolution NN is working. I don't see where I can set the number of filters. Okay, so try using the 2D convolution with 1 as the secondary dimension, but probably easier to just go to the NN documentation. How is it possible to layer-wise pre-train a neural network in Torch? So doing true pre-training. At this point, I'd like to just thank my colleagues who are also trying to answer some of these while I was actually talking. So doing true pre-training with generative models is more advanced for most users, but transfer learning is available. So you can load cafe models, but the load cafe import doesn't cleanly import the models. Okay, I'll move on from that one. Is distributed MPI-like neural network training available in Torch to offload computation to multi-GPU clusters? Yes, there is support for multi-GPU training within a node, but not inter-node support. Is Digits more likely to support Torch Next or Theano? Definitely Torch. We are working with all the frameworks, but I know we definitely want to get Torch fully integrated. I don't want to give out actual dates, but I would probably say within the next couple of months. We are very actively developing. What is the name of the system used for pedestrian detection and traffic sign recognition? Okay, so there's actually lots of studies on that subject. You can either go to Wikipedia or Sumith, sumith.ch. He has lots of pedestrian papers from CBPR, etc. Okay, I think probably one more question, and then we will wrap up. So can we run Torch models or code through Python commands? Yes, that can be done with the FP Lua-lib, for example. Have a look around on the actual GitHub at Facebook's main FBCUNN code. There's lots and lots of documentation on there. So I think at that point, I'd like to say thank you very much for listening. Massive thank to all my colleagues for the lab for helping me put that together, and also to my colleagues for helping on the questions. Thank you for your questions, and please use the resources that we'll put up on the deep learning site. Thank you very much.